Two stars exploded so brightly they could be seen with the naked eye. Two terrifying earthquakes tore through the bedrock of Venezuela, and an interstellar visitor flew by. Alaska was hit by a solar storm, all happening within just 72 hours. If this were a movie script, screenwriters would surely have to discard it, because the plot is unbelievably coincidental. Yet this is reality and the present, bringing us the most synchronized astronomical phenomena. In the modern era, after what just occurred, even the most rational people must wonder if we are witnessing something stranger than mere coincidence. Tonight, we will analyze each event with absolute precision, examining the scientific basis behind the fury of the stars and the subsequent planetary tremors, delving into a fragile boundary, where random coincidence intersects with the human pattern recognition mechanism. Stay tuned until the end, because what we discover about September 2025 may challenge everything we thought we knew about what is truly operating out there. Part 1. An extraordinary sequence of events. Two stars exploded. Two massive earthquakes tore through Venezuela's ground, and an interstellar visitor was swept by a coronal mass ejection. All these events happened just days apart at the end of September 2025. If you're starting to feel the universe is trying to send a message, you are not alone. Let's accurately review this dramatic cosmic sequence. On the 23rd of September, astronomers detected Vasi a 93 Centauri, a nova explosion in the constellation Sagittarius in the southern hemisphere, bright enough to be seen with the naked eye at magnitude 5.8. Just days later, another star explosion occurred at 794 Sagittarius, shining brightly in Sagittarius at magnitude 6.2. Both stars suddenly became visible to anyone willing to step outside and look up at the sky. Meanwhile, over 11,000 kilometers away at the nearest observatory, our planet was also shaking. At 22:21 UTC on 24 September, a magnitude 6.2 earthquake struck near Mana Grande, Venezuela, 24 kilometers northeast in the state of Julia, with the hypocenter just 7.8 kilometers deep. The tremors generated shock waves spreading across Venezuela and Colombia. But nature was not done yet. A few hours later, at 05:51 UTC on 25 September, a second earthquake of magnitude 6.3 occurred in the same area, this time with a hypocenter at 14 kilometers depth, two stars, two earthquakes, and high above, though invisible to the naked eye, but still monitored by satellites. Something else was happening. Forecasters at NOAA's Space Weather Prediction Center were tracking coronal mass ejections, CMEs, massive clouds of magnetized plasma weighing billions of tons, blasted from the sun at speeds exceeding 100,000 kilometers per hour. Their computer models showed these solar storms were on a collision course with an unprecedented object, asteroid Atlas, the third confirmed interstellar visitor to visit our solar system. This is when the timeline becomes dramatically, unbelievably synchronized. The discoveries of novas and earthquakes in Venezuela all clustered around 23 to 25 of September. Forecast models also showed solar storm activity peaking in the same period, and Atlas was discovered just 2 months earlier by the Asteroid Impact Warning System. Atlas is moving through the inner solar system during what may be the most active phase of solar cycle 25. The geographic locations of these events span scales that challenge human intuition. Novas exploded in the constellations. Sagittarius and Centaurus constellations, mainly observed from Earth's southern hemisphere. Their light traveled thousands of years to reach us during this special week. Earthquakes occurred near Mana Grande in northwest Venezuela, in a complex tectonic region where the Caribbean and South American plates collide and rub against each other. The coronal mass ejection from the Sun spreads throughout the inner heliosphere, a space larger than Jupiter's orbit, and Atlas is crossing the ecliptic plane, the imaginary disk where most planets orbit, gliding between Mars and the Sun. We do not claim this is a causal chain. That would be too soon and possibly reckless. What we are doing is reigniting clusters of events recording convergence and preparing to consider mainstream scientific explanations, alongside bolder hypotheses. The U.S. Geological Survey asserts there is no proven link between weather, space, and seismic activity. Solar physicists will tell you that coronal mass ejections are frequent phenomena of an active sun. Astronomers regard novae as predictable consequences, though the timing cannot be forecast, of binary star evolution. But this is what makes this week truly unique in modern astronomical history. Atlas is only the third confirmed interstellar object ever discovered, after Oumuamua in 2017 and Borisov in 2019. Even more interestingly, this is the first time we can witness an interstellar visitor affected by intense solar weather near the solar cycle maximum phase. We have precedents for what solar events can cause to comets in the solar system. In 2007, the European Space Agency's stereo satellites recorded a coronal mass ejection, severing the ion tail of Comet Encke, an event demonstrating the severity of space weather interactions and the importance of the coming months. Beyond mere academic curiosity, Atlas is expected to fly past Mars on 30 October, at a distance of 0.19 astronomical units, equivalent to about 28 million kilometers from the red planet. Mars orbiters including ESA's ExoMars and NASA's Mars Reconnaissance Orbiter are preparing to observe, to clarify details about the nucleus and coma of the interstellar visitor, with unprecedented resolution by the end of October. Specifically on 29th of October, Atlas will reach perihelion, meaning its closest approach to our Sun at about 136 astronomical units. This triggers what space physicists call the Russell-McLaren effect, a geometric change in the orientation of Earth's magnetic field, enhancing connectivity with solar wind disturbances from September to November, historically producing some of the most spectacular auroral displays and the most significant impacts of space weather on technology. Our promise to you is this: we will provide both clear scientific explanations and bold hypothetical scenarios, but we will label each accordingly. You deserve to know what is confirmed truth through observation, what is scientific speculation, and what is pure imagination. Data is important. Wonder is also important. To compare, this distance is even closer than Mars at its farthest point, offering many months of observation for both professional observatories and amateur astronomers with modest telescopes. This convergence occurs during a season when space weather tends to increase. This distance is still beyond Earth's orbit, but close enough for ground-based telescopes to study its composition and activity in real time. The viewing angle will be even more favorable on 19th of October 2025, when Atlas approaches Earth at about 1.8 astronomical units, Part 2 novae. Sudden explosions in the southern sky in the hours before dawn. On 23rd of September 2025, amateur astronomer John Seich was doing the work he has done for many decades, observing the southern sky from his observatory on Chestworth Island, New South Wales, hunting for stellar explosions. What he found that morning would soon attract the attention of gamma-ray satellites and telescopes across the solar system. About a 19th-century nova appearing not with a loud bang, but with the initial detection of bright photon lines by SID showing a star in a previously unremarkable position, suddenly brightening in the constellation of Sagittarius, with a magnitude of 5.8 to 6, just enough for keen-eyed observers in dark locations to detect it without binoculars. But this was not an ordinary flare-up. Within hours after SIS reported the discovery to the Astronomical Telegraph Center, space observatories began detecting something extraordinary. NASA's Fermi Gamma Ray Telescope recorded high-energy photons emitted from the direction of the Star Swift Observatory. Designed to hunt gamma-ray bursts, had turned its X-ray telescope towards the Sagittarius constellation and began recording hard X-ray radiation, a sign of particles being accelerated in the wide shock wave of the novae. These were not just beautiful lights for stargazers. This was evidence of physics operating at extreme limits. Electrons and protons accelerated close to the speed of light. Magnetic fields twisted into enormous energy knots. But V19b Centauri still attracted attention just a few days later. Lightning struck, or rather the universe did so. The star 5794, Sagittarius, exploded in the neighboring Sagittarius constellation, reaching a brightness of 6.2 when detected 2 nova explosions, both recorded by the same observer, both bright enough to be seen with a small telescope or binoculars, and both occurred within the same remarkable week. This is why this pair of stars amazed professional astronomers, although novae are not rare, with about 10 to 12 events occurring in our galaxy each year, but having 2 novae reach near naked-eye brightness within a few days is truly unusual. The last time observers witnessed 2 bright novae simultaneously was in summer 2023, and before that you have to go back many years to find similar displays. The physical mechanism behind these eruptions tells a story of interaction and engulfing of stellar material, occurring throughout cosmic time. Each nova begins with a white dwarf star, the dense, hot core of a dead star about the size of Earth, but with the mass of our Sun remains, orbiting a normal companion star, gradually accreting hydrogen gas from its outer atmosphere. Over years, centuries, or millennia, this gas accumulates on the white dwarf's surface, becoming denser and hotter under enormous gravitational pressure until temperature and pressure reach a critical threshold. The accumulated hydrogen undergoes an uncontrollable thermonuclear fusion reaction, not the stable burning process that powers stars, but an explosive outburst that can make the binary star system brighten by 10,000 times or more. The explosion does not destroy the white dwarf. Instead, it blows off the surface material, and the system patiently begins the accumulation process again. Some recurrent novae erupt predictably every few decades, Others may wait thousands of years between outbursts. The gamma ray and hard X-ray signals of V19b Centauri reveal the most violent aspects of a nova explosion as the thermonuclear blast ejects material at thousands of kilometers per second, creating shock waves, accelerating particles to enormous energies. These relativistic particles interact with magnetic fields and surrounding matter, producing high-energy photons that triggered the sensors of Fermi and Swift. These are also the physical laws at work in supernova remnants and active galactic nuclei. These cosmic particle accelerators transform ordinary matter into high-energy radiation. For observers in the southern hemisphere, both novae occupy prime viewing positions. The 19b Centauri lies near the celestial equator, making it a challenging target. In 1983, Centauri, located near the celestial equator, made it a difficult target for observers in the northern hemisphere who had to wait for it to rise above their southern horizon. Sagittarius, located in the constellation Sagittarius, also has a similar observational geometry in the south, appearing low in the south for observers at mid-northern latitudes, but high in the sky for anyone south of the equator. The discovery process itself revealed the collaborative nature of astronomy, modern real-time astronomy. The initial observations of Stitch, reported through the International Astronomical Union's Information Center, triggered a series of follow-up observations. Electronic Bulletin Number 5611 confirmed the discovery of V189b Centauri, while Bulletin Number 5612 recorded V7994 Sagittarius within a few days. Observatories worldwide obtained photometric data, precise brightness measurements, and spectral data, revealing the characteristic emission lines of hydrogen, helium, and heavier elements in the shell. Expanding novae, amateur astronomers play a vital role in nova science through organizations such as the SAO Observers Association, the American Association of Variable Star Observers, AAVSO, and their nightly monitoring, provide time series data with high resolution showing the light curves of how the nova develops complex patterns of outburst. Stable phases and gradual decline contain clues about the physical mechanisms of the explosion and the properties of the binary star system. Professional telescopes cannot continuously monitor every novae, but dedicated amateurs can track brightness changes nightly, contributing data that shape our understanding of these explosions. The naming conventions often confuse newcomers to astronomy. The 189b Centauri received its name because it is the 189th variable star. The 189b was officially named in the constellation of Sagittarius, while V7994 Sagittarius is the 7994th star in the Sagittarius constellation. These permanent names replace the temporary designations assigned at discovery, which can sometimes make timelines confusing. When objects discovered later receive earlier numbers due to administrative delays, processing both novae are expected to fade over the coming weeks and months according to typical decline, which can last from several months to years. However, their evolution may include surprises. Some novae develop dust formation phases, weeks after the explosion, temporarily dimming, as newly formed dust particles absorb and scatter their light. Other nova show complex multi-peaked light curves as different physical processes dominate at different times. A question space weather enthusiasts cannot help but ask is whether these stellar explosions occurring in the same week with significant geomagnetic activity is merely coincidence. From an orthodox astronomical perspective, the answer is clear. Stars in neighboring constellations are thousands of light-years from Earth. Their light poses no direct threat to our planet and does not measurably affect terrestrial phenomena. The energy from these explosions, though enormous by human standards, dissipates across the vast interstellar space, reaching Earth only as a slight increase in photons. Beautiful to observe, but harmless to experience. However, the timing coincidence remains remarkable. 2 stellar explosions in 1 week with 2 double earthquakes, along with an interstellar visitor passing through an active solar weather region. Perhaps the most honest response is to acknowledge both science and synchronicity, to understand the physical mechanisms while remaining open to the possibility that our universe sometimes arranges itself in ways that make coincidence almost poetic. Meanwhile, any observatory capable of detecting these spectacular fireworks, more than 11,000 kilometers, the solid ground beneath Venezuela, is about to prove that explosions are not limited to distant suns. Part BA of the earthquakes in Venezuela, precisely at 22:21:55 UTC on 24/9. The Earth's crust beneath the Julia Plain in Venezuela released an energy source equivalent to many nuclear weapons. A 6.2 magnitude earthquake occurred near Monte Grande, 24/9. To the east-northeast, originating from a relatively shallow depth of 7.8 km, close enough to the surface to cause buildings to shake across 2 countries. Seismic waves spread out at about 6 km per second through the bedrock, reaching populated areas within seconds after the fault rupture occurred, from Maracaibo to Caracas, from border towns with Colombia to Caribbean coastal cities. Millions of people felt the ground shaking beneath their feet. Social media flooded with videos of chandeliers swinging, windows rattling, and people evacuating buildings, as emergency procedures were activated across the region. But the Earth had not stopped. Only 5.5 hours later, at 03:51:39 UTC on 25/9, a second major earthquake occurred at almost the same location. This time, a 6.3 magnitude earthquake originating from a depth of 14 kilometers, deeper than the previous one, but still shallow enough to create strong surface shaking. The epicenter was about 27 to 28 kilometers northeast of Monte Grande, coinciding with the fault area of the first earthquake. To understand why this earthquake pair is important, we need to understand the logarithmic nature of the intensity scale. A 6.3 magnitude earthquake releases approximately twice the energy of a magnitude 6.2 magnitude earthquake combined. These 2 faults generated energy equivalent to an earthquake, with a magnitude between 6.4 and 6.5, a significant energy release, even by global standards. The events of 24th and 25th of September represent the largest seismic activity in the region since the 7.8 magnitude Kamchatka earthquake on 18/9, placing Venezuela's earthquake pair among the most notable global seismic events. By the end of September 2025, the aftershock sequence also created its own drama. A 5.8 magnitude earthquake struck the same area later on 25/9 UTC time, following a typical Omori decay pattern expected by seismologists after major faults. Although 5.8 magnitude seems modest compared to the main shocks, it was still large enough to cause additional damage and maintain anxiety levels in an already stressed community. Regional tectonics explain why this area has the potential to produce such strong earthquakes. The Maracaibo Trough lies in a complex zone where the Caribbean plate collides with the South American plate, creating a network of fault systems including the Bocono Fault and faults trending Santa Marta Bucaramanga. These geological boundaries have accumulated pressure over many years, decades, even centuries, storing energy that must eventually be released through sudden slip events, i.e. earthquakes. The difference in depth between the two main events, 7.8 versus 14 kilometers, is significant for the intensity of ground shaking. Shallow earthquakes usually produce stronger surface acceleration compared to deeper earthquakes of the same magnitude, because seismic waves have less distance to dissipate and weaken on their way to the surface. The shallow focal depth of the 24/9 event likely contributed to widespread reports of strong shaking across Venezuela and Colombia. Various seismic agencies reported slightly differing intensities for these events, reflecting the complexity of earthquake measurement. The U.S. Geological Survey initially reported the first earthquake at a magnitude of 6.2, while the European Mediterranean Seismological Center and other international monitoring networks gave measurements ranging from 6.1 to 6.3. These differences arise from many factors, including different measurement methods, updates as more data from seismic stations become available, and differences between moment magnitude, surface wave magnitude, and body wave magnitude calculations. The impact of these earthquakes on people far exceeded seismic statistics. Evacuation orders affected thousands of residents, especially those in high-rise buildings who experienced prolonged shaking during the event. Emergency response teams were mobilized across the region to quickly assess the damage and ensure that critical infrastructure such as hospitals, bridges, and power plants remained operational. While initial reports indicated that structural damage was relatively limited compared to the earthquake's intensity, assessment teams continued their work for several days afterwards to record both visible damage and potential longer-term structural weaknesses. Historically, this area has experienced significant seismic activity, with a complex geological tectonic system around Lake Maracaibo and the broader boundary of the Caribbean and South American plates frequently generating sequences of earthquakes. Although large magnitude events like this are not common, geological records show that major faults in this region can sometimes trigger additional activity on neighboring fault segments. This process is known as stress transfer, which occurs when an earthquake alters the stress field on adjacent fault systems. The timing of these events has raised many questions for both professional seismologists and the public about whether more large earthquakes could occur. The answer, based on the complex statistics of aftershock sequences, is that aftershocks are expected and completely normal, with the largest aftershocks usually occurring within days to weeks following the main earthquake. However, seismologists cannot reliably predict whether an even larger earthquake might occur in the same area in the short term. Earthquake forecasting science remains a major challenge, despite decades of research on foreshocks, stress accumulation patterns, and statistical forecasting methods. International monitoring networks have tracked each aftershock, creating a picture of how the fault systems respond to stress changes caused by the two major fault ruptures. The Global Seismic Moment Tensor Database has begun processing detailed analyses of fault orientation, slip direction, and rupture mechanisms for both events. This company helps seismologists understand which fault segments actually slipped and how the stress field changed across the wider region. For residents of Zulia State and neighboring areas, this earthquake pair is a harsh reminder of the geological reality in their region. Building regulations, emergency preparedness, and community response systems all face challenges during such events. The relatively moderate damage reports, given the earthquake's intensity, may reflect some luck in timing. The events occurred at hours when many people were at home rather than in more vulnerable workplaces, and ongoing improvements in building standards and response capabilities. A bigger question arising from these events relates to their timing, compared to other phenomena occurring in the same remarkable week. Seismologists affirm that no physical mechanism has been proven to link solar activity, space weather, or astronomical events with earthquake occurrences. The official stance of the U.S. Geological Survey emphasizes that correlations between weather, space conditions, and seismic activity remain unproven despite periodic claims in both scientific literature and popular media. However, the human mind naturally tends to seek patterns, especially when dramatic events occur close together, such as a pair of novae, a pair of earthquakes, active solar weather, and an interstellar visitor passing through the inner solar system. This convergence seems to carry some significance even if the mechanisms remain unclear. Perhaps the most honest scientific approach is to record the timeline, study each phenomenon independently, and remain open to exploring connections, while avoiding premature causal attributions based solely on correlation, as aftershocks continue to shake Venezuela. The Sun is also preparing to demonstrate that near-Earth space can be just as dynamic as its solid surface. Part 4. The flames from the Sun, 150,000 km away from Earth, are shaking Venezuela. Our host, Star, is also performing its own explosive symphony. On days when star explosions light up the southern sky and earthquakes tear apart the South American bedrock, the Sun has released coronal mass ejections. Clouds of plasma weighing billions of tons will cross the path of an object, unprecedented in human experience, an interstellar visitor. Coronal mass ejections shimmer, representing some of the most powerful events in our solar system. These eruptions originate from the Sun's corona, where magnetic field lines are twisted, bent, and eventually snap like overstretched rubber bands. When magnetic reconnection occurs, it releases an energy source equivalent to billions of Hiroshima bombs. Plasma speeds reach from 250 to 3,000 kilometers per second, fast enough to cover the distance to Earth in just 1 to 4 days. The NOAA Space Weather Prediction Center tracks these solar storms using the WSA and LU model, a complex computer simulator to map how coronal mass ejections spread through the heliosphere. This model considers solar wind speed, density, and magnetic field direction to forecast when and where these plasma clouds will intersect spacecraft, planets, and other objects along their path. By late September 2025, NOAA's forecasts show space weather conditions are highly active, with many CME events crossing the inner solar system on the very days that brought us a pair of novae and a pair of earthquakes. But here is the point that makes this story unique in history for the first time in recorded human experience. One of these solar storms is on course to collide with an object originating from another star system, an interstellar visitor, discovered only 2 months earlier by the asteroid impact warning system Atlas, moving through the inner heliosphere amid some of the strongest activity of solar cycle 25. This interstellar visitor moves on a retrograde orbit inclined about 175 degrees relative to the ecliptic plane, crossing the same space region that Earth orbits, a privileged position to encounter solar weather phenomena. We have precedent for what happens when coronal mass ejections collide with comets. This interaction is not speculation, but a physical process recorded by spacecraft and analyzed in scientific literature. In 2007, the European Space Agency's stereo satellites captured a CME, completely severing the ion tail of comet Encke. This disconnection event, lasting several hours, demonstrated the violent reality of a magnetic reconnection between plasma from the Sun and cometary material. Comet tails form through 2 distinct processes, and each type reacts differently to the Sun's influence. The dust tail gracefully curves and is pushed away from the Sun by radiation pressure, a gentle but persistent force of sunlight acting on dust particles. By contrast, the ion tail is pulled straight away from our star, following the magnetic field lines of the solar wind. When a coronal mass ejection disrupts these magnetic connections, the tail can completely detach, drifting away from the comet and eventually dissipating, while a new tail forms from fresh material. The claim that Atlas was hit by a CME is based on orbital analysis by modeling, not direct observation. NOAA's forecast suggests the solar storm will cross the path of the interstellar visitor at the end of September. But we must be transparent about this uncertainty. Space weather models are excellent at predicting general trends, but struggle with fine details. So this interaction remains an inference based on forecasts, rather than a confirmed discovery. If the interaction truly occurs as models have suggested, we can expect some observable consequences. Increased ionization could brighten the gas envelope of the object up to the comet. That is, the open atmosphere of gas and dust surrounding its nucleus. Changes in the morphology of the ion tail may appear in telescope images, when magnetic disturbances alter how charged particles escape from the object. Spectral observations can reveal chemical signatures. When solar energy releases specific molecules such as CN, CO, and CO2 from the ancient ice layer of the strange object, amateur astronomers worldwide are ready to record any such changes. A global network of comet observers, connected via online forums, and observing organizations maintain nightly image records of interesting objects. Their images, when compared over time, can show subtle changes in brightness, tail structure, and comet head morphology that often escape detection by observatories, professional ones focusing on other targets. The physical mechanism of this interaction is magnetic reconnection, the same process causing solar flares and geomagnetic storms. When solar plasma carries magnetic field lines, tangled magnetic fields encounter the comet's ionosphere. Field lines can connect, disconnect and reconnect, releasing energy that accelerates particles and creates observable phenomena. It is an elegant physical mechanism where magnetic structures change in real time, converting stored magnetic energy into kinetic energy of charged particles. Atlas is not just an ordinary target for weather interactions. The Sun is the second confirmed interstellar object after Oumuamua in 2017 and Borisov in 2019. It carries matter formed around another star, in another star system possibly billions of years ago. If solar storms can alter its behavior, we are witnessing the first recorded case of our Sun directly interacting with matter from another star system. The orbit of this strange object makes such interactions more likely to occur than with previous interstellar objects, unlike Oumuamua, which passed quickly through the inner solar system and at a high inclination to the plane. Atlas follows an orbit keeping it closer to this plane. This is the plane where solar activity tends to concentrate, and where the Earth experiences most space weather impacts. Solar Cycle 25 has provided a strong activity background. For these interactions, the Sun's 11-year cycle reached its maximum phase in 2024 and 2020, producing a high number of sunspots, increased frequency of flares, and more frequent coronal mass ejections. The timing of this cycle means Atlas is experiencing our star at its most active state enduring space weather conditions that previous interstellar visitors missed. Verifying by observing shimmer interactions requires careful analysis of brightness changes, spectral variations, and morphological evolution over timescales from hours to days. Observatories, professional and amateur worldwide, have monitored Atlas throughout late September, although results remain preliminary. As analysis continues, broader implications extend beyond this single event. If we can record how our Sun affects interstellar matter, we will gain insight into similar processes occurring throughout the cosmos. Other star systems may also emit their own coronal mass ejections, potentially altering interstellar objects passing through their neighborhood. Atlas may carry signatures of interactions with previous star systems it encountered on its millions of years journey through space. As September 2025 gradually comes to a close, the convergence of events of star explosions, earthquakes on Earth, solar storms, and interactions with a visitor from space has created a challenging timeline to the usual assumptions about random coincidences in the universe. Are we witnessing unrelated phenomena, coincidentally converging, or is there something more systematic happening? The answer will gradually be revealed as the Atlas mission continues its journey towards a flyby of Mars on 3/10, bringing along any changes that coronal mass ejections from the Sun may have impacted it. Part 5 of the coincidence, or a hidden law. Let's take a step back and consider what we have recorded. A pair of binary stars exploded so brightly they could be seen with the naked eye. 2 magnitude 6 earthquakes occurred just hours apart. Coronal mass ejections swept through the inner solar system. An interstellar visitor passed through our region during the Sun's most active period. Many cosmic events happened in rapid succession, compressed into the last week of September 2025. This is where genuine science meets the human ability to recognize innate patterns, and this collision is not always pleasant. Our brains have evolved to detect meaningful connections in a complex environment. Rustling sounds may signal a predator. Cloud formation may signal rain. Changes in behavior may indicate a threat, or social opportunity and structure. This perception serves us well in many contexts, but it can also make us see meaning in random coincidences. Mainstream science provides clear guidance on these events. The U.S. Geological Survey does not recognize any proven links between weather phenomena, space events, and the occurrence of earthquakes over decades. Correlation studies have failed to establish reliable predictive relationships between solar activity and seismic events. Professional seismologists emphasize that earthquake prediction remains impossible with current scientific methods, whether based on terrestrial foreshocks or external influences. Similarly, astronomers regard novae as predictable consequences of binary star evolution when a white dwarf accumulates enough material from its companion star to trigger a thermonuclear reaction. The timing of a nova eruption follows stellar physical laws, not due to influences from Earth or the solar system. V Alpha Centauri and V7994 Sagittarius represent typical, though visually impressive, examples of processes that occur frequently throughout our galaxy. Solar physicists study coronal mass ejections as natural consequences of magnetic field evolution in the Sun's corona. These events occur more frequently during solar maximum, making late 2025 a statistically high probability period for many such events. The interaction between solar storms and cometary material has been widely documented, representing a well-understood plasma physics process, not a strange phenomenon. However, accepting mainstream scientific views does not require us to dismiss the remarkable nature of this cluster of events. Sometimes the universe arranges itself in ways that push coincidence close to the threshold of synchrony, even when underlying mechanisms remain normal. The question posed is, how do we balance skepticism, rigorous science, and inherent wonder? Our approach throughout this exploration will be to maintain clear boundaries between different types of claims: observable events, measured magnitudes, coordinates, detection locations. Spectra form our foundation. They represent what instruments have recorded, what satellites have detected, and what seismometers have measured on this basis. We will build scientific interpretative layers based on established physics and verified models beyond established science. There is also the realm of speculation, where we will venture carefully and with clear notes on speculative correlations, possible relationships between solar activity and terrestrial phenomena, the potential impacts of subsequent events on the dynamics of the solar system. All these assumed mechanisms are worth exploring as long as we are transparent that they remain hypotheses rather than facts. Vocabulary about cosmic events needs to be defined for the general audience. A nova represents a star explosion. It is a binary star system that brightens thousands or millions of times, caused by uncontrolled nuclear fusion reactions on the surface of a white dwarf star. It is fundamentally different from a supernova, which completely destroys a star. A coronal mass ejection, CME, involves billions of tons of plasma clouds, ejected from the Sun at speeds of hundreds to thousands of kilometers per second. Perihelion is the closest distance of an object to the Sun. In its orbit, an astronomical unit, AU, equals approximately the average distance from Earth to the Sun, about 150,000 kilometers. Ion tail forms when the solar wind strips electrons from gas molecules in the comet's head. The tail creates charged particles that follow magnetic field lines extending away from the Sun. These tails can stretch millions of kilometers into space. What is coming next in our investigation will separate observed phenomena from imaginative connections while still respecting both scientific rigor and human curiosity. We will examine in detail the physical mechanisms of stellar explosions, earthquakes, and solar storm interactions. We will follow the Atlas mission during its flyby of Mars on 310, and as it approaches perihelion on 2910, we'll explore reasonable scientific hypotheses about the connections between cosmic and terrestrial phenomena, along with speculations clearly noted about stranger possibilities beyond traditional analysis, usually amplifying space weather effects through the Russell-McLaren effect, a geometric combination of Earth's magnetic field and solar wind conditions, often enhancing geomagnetic activity in September and October. This seasonal enhancement provides additional context to explain late September solar activity, which can create heightened space weather activity independently of any connections to other phenomena. The Atlas mission offers unique scientific opportunities precisely because it is our confirmed third visitor to Mars and the first observed under conditions of strong solar activity. Its orbit passes near the ecliptic plane, where most solar system activity is concentrated, helping maximize observation and interaction opportunities with space weather. Unlike Oumuamua, which quickly departed before comprehensive study, or Borisov, still relatively distant, the Atlas flyby provides extended observation opportunities over many months. The importance of October and November goes beyond academic interest. Mars orbit missions include the Mars Atmosphere and Volatile Evolution, MAVEN Orbiter of ESA, and NASA's Mars Reconnaissance Orbiter MRO, planned to observe during its flyby on 310, potentially providing unprecedented high-resolution images of the nucleus and dust shell of this interstellar object. Ground-based observatories worldwide continue to monitor brightness changes, spectral evolution, and morphological variations, which may reveal how solar weather affects interstellar matter. Regarding earthquake monitoring in Venezuela, aftershocks often continue for weeks to months following major fault ruptures. Although seismologists cannot predict whether larger events may occur, they maintain continuous monitoring of seismic activity in the region and the evolution of the stress field. The complexity in the tectonics of the Caribbean-American plate boundary ensures that this region will continue to generate earthquakes, although the exact timing of these events remains essentially unpredictable. Our commitment is to present all viewpoints honestly. Mainstream scientific explanations deserve top priority because they are based on established physical foundations and supported by extensive observations. Speculative hypotheses are also worth considering as long as they are clearly distinguished from science. It has been proven that the instinct to seek meaning in human patterns is worthy of respect even when scientific evidence does not support causal connections. Perhaps the most remarkable aspect of this convergence relates to the very time we are living in. The first generation in history, humanity has the ability to detect guests arriving at stars, monitor global seismic activity in real time, observe stellar explosions across the electromagnetic spectrum, and monitor space weather throughout the entire solar system. Previous generations may have noticed new stars lighting up and felt the ground shake, but they could not connect these phenomena with storms, the sun, and guests arriving at stars simply because the technology to do so did not exist. We will separate what is observed from what is imagined, what has been proven from what might happen, and what is likely to happen from what lies only in the imagination. So how can stars explode? Without completely self-destructing, the answer reveals a physical mechanism operating on scales that challenge human intuition. Part 6. Decoding a nova. Imagine a white dwarf star, a celestial body only the size of Earth but compressed tightly, containing the mass of our entire sun. Its surface gravity compresses matter to a density nearly 1,000 times that of water, with surface temperatures around 27,000 degrees C. This star is what remains after a sun-like star exhausts its nuclear fuel, blows off its outer layers, and collapses into a degenerate mass. This cosmic furnace is locked in a delicate dance with a normal companion star, perhaps a red giant star, with an atmosphere swollen to giant proportions as it ages. The gravity from the white dwarf gradually strips hydrogen gas from the companion star's atmosphere, pulling the gas through space into swirling streams like water spiraling down a drain. This stolen material accumulates on the surface of the white dwarf, becoming denser and hotter under the compression of gravity over tens of millennia, or even millennia. Hydrogen continues to accumulate. Temperature and pressure steadily increase as more matter piles up on the white dwarf's surface, unlike controlled nuclear fusion reactions occurring in the core of a star. This process leads to an explosive release of energy. When temperatures reach about 100,000 degrees Kelvin, an uncontrolled thermonuclear reaction begins. The explosion, creating a nova in Centauri, occurred in just a few seconds. The uncontrolled nuclear fusion reaction consumed the entire hydrogen layer, accumulated in a giant fire, releasing energy equivalent to the sun's total output over thousands of years. But here is the important difference. Compared to a supernova, the white dwarf star remains intact. The explosion only blows away the surface layer of stolen material, leaving the underlying star residue intact and ready to begin the process again. This is why stars, the high-energy signals from the nova in Centauri, attracted the attention of space observatories worldwide when NASA's Gamma-ray Space Telescope detected gamma rays from the direction of the nova. This is evidence of particles accelerated close to the speed of light in the shock waves of the explosion. The Swift Observatory detected high-energy X-rays, showing electrons spiraling in magnetic fields with enormous energy. Producing synchrotron radiation across the electromagnetic spectrum. These high-energy phenomena transform pulsars from simple brightening events into particle accelerators. Cosmic ray particles in the shell of matter are ejected at speeds of thousands of kilometers per second, creating shock waves as it collides with the diffuse interstellar gas. These shock waves act like natural particle accelerators, using magnetic acceleration to propel protons and electrons to energy levels that only giant laboratories on Earth can achieve. The American Association of Variable Star Observers, AAVSO, combines contributions from amateur astronomers and science on novae through standard photometric measurement procedures. Observers with the naked eye estimate brightness by comparing with standard stars, while CCD cameras provide precise brightness measurements, revealing subtle variations in the light curve of novae. These observations are contributed by hundreds of amateur astronomers worldwide, providing time resolution that professional observatories cannot maintain for individual objects. The brightness evolution of V1974 Cygni follows models established through many decades of nova research. The initial rise from invisibility to visible brightness usually occurs over several days to weeks. The peak brightness can last from several days to months, depending on the mass of the white dwarf, the accretion rate, and the composition of the ejected material. The decline phase can last months or years, sometimes interrupted by secondary brightness peaks when different physical processes dominate. Spectra reveal the chemical fingerprints of novae. Initial spectra often show broad emission lines of hydrogen, helium, and heavier elements moving at high velocities, evidence of expanding material as the nova evolves. These lines narrow and shift as the ejected material cools and slows down. Finally, forbidden lines appear, which are atomic transitions that can only occur in the extremely rarefied environment of the expanding nova shell. Distances to V1974, Cygni, and V7994 Sagittarius remain uncertain but probably exceed several thousand light-years. This means the explosions we observe in 2025 actually occurred millennia before human civilization began developing agriculture. Light from these later explosions has traveled through space longer than the recorded history of humanity to reach Earth precisely during this remarkable week. Amateur astronomers can contribute meaningful observations using modest equipment. A DSLR camera with a telephoto lens can capture both novae at their brightest phases. Naked-eye observers using binoculars or small telescopes can estimate brightness by comparing the novae with nearby stars of known brightness. More advanced observers with CCD cameras and photometric filters can provide accurate data, supplementing professional observations. The naming system for novae reflects astronomical tradition and administrative processing. V974. Cygni received its permanent variable star designation, as it was the first nova officially catalogued in the constellation Cygnus. The prefix Vive denotes a variable star, an object whose brightness changes over time. This permanent designation replaces temporary names assigned at discovery, which may include the discoverer's name, or catalog numbers from survey programs. Dust formation represents one of the most interesting aspects in the evolution of novae, weeks to months after the explosion. Some novae undergo significant dimming as new dust grains form and condense in the cooling ejected material. These dust-dimming events can reduce the nova's brightness by several magnitudes, as dust grains absorb and scatter its light. Eventually, this dust layer is either dispersed or destroyed by ongoing radiation, allowing the underlying stellar remnant to reappear. The energy scale involved in nova explosions, though dazzling to humans, remains modest compared to supernovae. A typical nova releases energy equivalent to the total output of the Sun over about 10,000 years. However, this is only a very small part of the energy released. In supernova explosions, which can be brighter than an entire galaxy for weeks or months, recurrent novae complicate the picture of single explosion events. Some white dwarf star systems undergo relatively periodic nova eruptions, predictable every few decades for the most frequently recurring stars. These systems can experience dozens of explosions gradually, accumulating enough material to reach the Chandrasekhar mass limit at that point. The white dwarf star will explode as a type Ia supernova, Professional observations continue to monitor both September novae across many electromagnetic wavelengths. Ground-based telescopes monitor changes in optical brightness and spectral evolution. Space observatories, including the Hubble Space Telescope, can obtain high-resolution images of the expanding nova shell. Radio telescopes can detect synchrotron emission from relativistic particles in the ejected material of V1974, Cygni, and V7994 Sagittarius, classified as classical novae rather than other types of stellar explosions, based on spectral evidence and brightness changes over time. Novae are always caused by instabilities in the accretion disk, rather than thermonuclear explosions which usually show different spectral features, and less brightness increase than red, luminous stars possibly caused by stellar mergers, which show different colors and evolutionary timescales. Could one of these novae represent something stranger than standard thermonuclear explosions? Current observational evidence supports the classical nova interpretation, but astronomy always maintains a healthy skepticism about initial classifications. As more data is accumulated from multi-wavelength observations, detailed physical mechanisms may reveal subtle points, helping us better understand these specific explosions. The detection of gamma rays from V1974 Cygni placed it in a newly emerging class of gamma-ray novae, challenging traditional physical models. This high-energy radiation shows particle acceleration processes operating much more efficiently than previously thought possible in the nova environment. This mechanism may involve magnetic reconnection or shock acceleration, bridging the gap between nova explosions and higher energy phenomena such as supernova remnants, as we track these later explosions across the electromagnetic spectrum from Earth's solid surface, also about to show its own intense activity. Part 7. Decoding an earthquake sequence beneath Lake Maracaibo and surrounding areas in the state of Zulia. Venezuela is one of the most geologically complex regions in South America. The Caribbean plate rubs against the South American plate along a boundary zone, including many fault systems such as the Bocono Fault, Oca Ancon Fault, and Santa Marta Fault. These geological boundaries have accumulated stress over many decades, storing energy, which will eventually have to be released through sudden slip events. A magnitude 6.2 Richter earthquake at 22:21 UTC on 24/9 began with a crack along one of these fault segments at a depth of about 7.8 km. At this relatively shallow depth, seismic waves have little chance to dissipate and weaken on their way to the surface, increasing ground acceleration over a wide area. The initial crack probably extended several kilometers along the fault surface with sudden displacement measured in meters, releasing stress accumulated over many years. Seismic waves spread, radiating outward from the fault zone at about 6 km per second. Primary waves, P waves, compressional disturbances, arrived first at seismic stations in the area, followed by secondary waves, S waves, causing horizontal shaking motion usually responsible for the greatest damage to structures. Finally, surface waves move more slowly but often carry the most destructive energy, causing rolling motions described by witnesses as lasting several minutes. Only 5.5 hours later, at 03:51 UTC, on 25/9, a second major earthquake occurred in almost the same area. This magnitude, 6.3, earthquake originated from a depth of 14 kilometers, deeper than the previous one, but still shallow enough to create strong surface shaking. The second event likely occurred on an adjacent fault segment, triggered by stress changes caused by the initial rupture. This stress transfer mechanism explains why earthquakes often occur in clusters. When a fault segment suddenly slips, it alters the stress field. On neighboring fault segments, some areas experience increased stress, making them more prone to rupture, while other areas are relieved of stress. Clearly, the rupture on 24/9 added stress to the fault segment that failed. 5.5 hours later, the magnitude difference between the 6.2 and 6.3 events seems small, but the logarithmic nature of the scale means the second event released nearly twice the energy compared to the first event combined. These fault segments generated energy equivalent to an earthquake from magnitude 6.4 to 6.5, a significant energy release and one of the largest seismic events worldwide. At the end of September 2025, international seismic agencies reported slightly different magnitudes for these events, reflecting the complexity of measuring earthquakes. The U.S. Geological Survey uses the moment magnitude scale calculated from total energy released, while other centers may use different scales based on surface wave or body wave amplitudes. These methodological differences, combined with updates as more data becomes available, explain why magnitude reports range from 6.1 to 6.3 for the first event. The aftershock sequence follows models recorded over many decades. A magnitude 5.8 earthquake occurred subsequently on the 25th, which is a typical large aftershock, smaller than the main shock, but still strong enough to cause additional damage and concern. Omori's law, formulated in the early 1900s, describes that aftershock frequency decreases over time following major earthquakes. The largest aftershocks usually occur within days after the main shock, with smaller events continuing for weeks, months, or even years. The impact of these earthquakes spread across Venezuela and Colombia, the relatively shallow depth amplified surface shaking, leading to evacuation orders for high-rise buildings in major cities. Social media flooded with videos of chandeliers swinging, windows rattling, and people evacuating buildings. As emergency procedures were activated across the region, although initial damage reports were limited. Compared to the earthquake's intensity, assessment teams spent several days documenting both visible structural damage and potential long-term weakening of buildings and infrastructure. Regional geology helps explain why this area produces such strong earthquakes. The Maracaibo Basin formed through complex interactions between the Caribbean and South American tectonic plates. The Maracaibo Lake itself lies within a graben system, a down-dropped block bounded by faults, which continues to experience active deformation. The oil fields making this area economically important were also formed in sedimentary basins caused by the tectonic processes generating earthquakes. Depth measurements have significant uncertainties, especially in geologically complex areas. Depths of 7.8 kilometers were reported for the first event, and 14 kilometers for the second, are the best estimates based on seismic wave arrival times at monitoring stations. These depths place both earthquakes in the upper crust, where brittle faulting dominates over ductile deformation, which occurs at greater depths. The timing of these events raises questions about potential triggers such as solar activity or atmospheric pressure changes. Scientific consensus supported by the U.S. Geological Survey holds that no reliable correlation exists between weather, space, and earthquake activity based on decades of statistical analysis, has not been able to establish a predictive relationship between solar storms and seismic events. However, some studies have explored more subtle potential connections. Changes in atmospheric pressure can alter the stress on fault systems, with a small amount, usually much less than the pressure changes, caused by tides generated by the moon and the sun. Although these effects can be detected, they are still many orders of magnitude smaller than the stress changes required to trigger earthquakes on faults not close to the failure threshold. The Global Focal Mechanism Tensor Database provides detailed analysis of fault orientation, slip direction, and faulting mechanism for both earthquakes in Venezuela. These focal mechanism diagrams show which fault planes actually moved and in which direction. This information helps seismologists understand regional stress fields and predict which fault segments may be at higher risk in the future. Currently, statistical seismology is the only reliable method to forecast earthquake risk, and the probability of other major events in the same area will temporarily increase following large earthquakes such as those in Venezuela, due to aftershock activity and stress transfer effects. However, this increase usually lasts only a few weeks to months, and it is not possible to precisely determine when or where another earthquake might occur. Building codes and emergency preparedness systems face continuous testing in seismically active regions like Julia State. The relatively light damage after magnitude 6.2 and 6.3 earthquakes is probably due to a combination of luck and ongoing improvements in building standards. Modern earthquake-resistant building codes require structures to withstand strong shaking. Although older buildings may still be damaged or collapse, whether a larger earthquake will occur in the same area. The geological context certainly allows stronger events to happen. The fault systems around Lake Maracaibo historically have produced earthquakes as strong as magnitude 7 on the Richter scale, and regional tectonics indicate such events will continue to occur irregularly over geological time. However, seismologists cannot predict whether it will take days, years, or tens of millennia before the next major fault rupture occurs. The geology of Venezuela shows geological processes can release significant energy within a human timescale, while still obeying the physical laws operating over geological time. Pressure accumulates slowly as tectonic plates slide past each other at a rate of a few centimeters per year. When the pressure exceeds the tolerance limit, a sudden fault rupture releases the stored energy, accumulated over tens of millennia or centuries in just a few seconds to minutes. Violent shaking as aftershocks continue to shake the Caribbean-American plate boundary. Our attention now shifts to outer space, where another type of energy release is occurring on a much larger scale. Part 8. The Sun at Solar Maximum. The 25th solar cycle reached its peak. Activity during 2024 and 2025 transformed our originally mild star into a continuously active fireball, capable of ejecting plasma clouds weighing billions of tons throughout the solar system. On 24 and 25 September, when a solar flare lit up the southern sky and earthquakes shook Venezuela. Solar activity indices painted a picture of a star nearing the peak of radio flux at 10.7 centimeters, an important indicator of solar activity level, fluctuating around 180 to 190 solar flux units SFU at the end of September. This measurement is taken daily and closely correlates with the number and intensity of active regions on the solar surface. Values above 150 usually indicate high solar activity, while indices above 200 indicate very dynamic conditions, capable of causing major space weather events themselves. Sunspots have told the story of magnetic chaos occurring on the surface. The dark regions are often larger than Earth, forming places where strong magnetic field lines penetrate the surface and block normal heat convection. The magnetic field intensity in the core of sunspots can exceed 3,000 Gauss, about 6,000 times stronger than Earth's magnetic field. The more sunspots there are, the greater the chance for magnetic field lines to twist, reconnect, and release energy explosively in the form of solar storms and coronal mass ejections, CMEs. However, counting the number of sunspots only reveals part of the complexity of solar maximum conditions. The sun's magnetic field acts like a tangled mess, twisted rather than a relatively simple dipole field as during solar minimum. Active regions, that is, groups of sunspots, are connected by magnetic loops that can last for weeks or months, orbiting the solar disk and occasionally producing spectacular eruptions. Coronal mass ejections. CMEs represent the most impressive expression of solar maximum activity. These events begin when magnetic field lines in the corona twist and become so stressed that they suddenly break and reconnect, converting magnetic energy into kinetic energy of charged particles. This process ejects plasma masses, weighing billions of tons into space at speeds of 250 per second for slower events, up to over 3,000 kilometers per second for the fastest eruptions. The NOAA Space Weather Prediction Center tracks these solar storms using the WSA Enlil model, a sophisticated computer simulation mapping the propagation of CMEs through the heliosphere. This model divides space into a three-dimensional grid, calculating solar wind speed, density, and magnetic field direction changes as plasma clouds move through the solar system. Although Enlil is very good at predicting arrival times and overall intensity, it cannot capture every detail of CME structure at the time of arrival. Space weather effects are often amplified by a phenomenon called the Russell-McFerran effect. This geometric alignment arises from the orientation of Earth's magnetic field relative to the interplanetary magnetic field carried by the solar wind. During periods near the equinox, this geometry favors magnetic reconnection between the solar wind and Earth's magnetosphere, often producing more intense geomagnetic storms. Space weather dynamics extend far beyond auroral phenomena. Geomagnetic storms can disrupt high-frequency radio communications, forcing satellite operators to adjust orbits and, in extreme cases, threaten the stability of power grids. NOAA maintains scales for geomagnetic storms, G-scale, solar radiation storms, S-scale, and radio blackouts, R-scale, to help industries prepare for and respond to interactions between CMEs and solar energetic particles, SEPs, providing a natural laboratory to study plasma physics. The ion tail of a comet forms when the solar wind strips electrons from gas molecules, creating charged particles that follow magnetic field lines straight away from the sun. These tails can extend millions of kilometers, providing tangible evidence of invisible magnetic processes at work. When a CME encounters a comet, the interaction can become highly dramatic. The European Space Agency's Stereo satellite recorded such an event in 2007, when a CME completely severed the ion tail of Comet Encke through magnetic reconnection. The detached tail drifted away from the comet for several hours, while a new tail formed, demonstrating the dynamic nature of space weather interactions. The Sun reaching peak activity in 2020 has created a lively backdrop for the Atlas mission as it approaches the inner solar system. Unlike previous interstellar visitors that encountered the Sun during quieter periods, this object has previously encountered the Sun during a quieter period. This object has undergone space weather effects at nearly peak intensity. The combination of increased Siam frequency and the visitor's orbit, lying in the ecliptic plane, has maximized the likelihood of significant interactions. The physical mechanism of shimmer propagation involves complex magnetohydrodynamics, operating on scales from the motion of individual particles to larger structures including planetary orbits. Faster streams can overtake slower solar wind streams, creating compression regions and shock waves, helping accelerate particles to high energies. Many streams can interact with each other, merging into larger turbulences or creating complex magnetic field configurations. Professional space weather forecasters monitor multiple data sources to oversee solar activity and predict impacts on Earth. The Solar Dynamics Observatory (SDO) provides continuous images with high resolution of the surface and solar corona. The Solar and Heliospheric Observatory (SOHO) tracks coronal mass ejections. CMEs, the Advanced Composition Explorer (AC) probe, positioned between Earth and the Sun, provides early warnings of upcoming solar wind disturbances. Operators of amateur radio act as an informal global network to monitor the effects of space weather on Earth. Radio wave propagation at high frequencies varies significantly during geomagnetic storms, and their real-time reports supplement official measurements. The current solar maximum appears to follow a double peak pattern, seen in several previous cycles, with an initial peak activity in 2024, followed by sustained high activity through 2025. This means the risk of severe space weather is elevated, potentially prolonged, maintaining favorable conditions for impressive interactions. Until 2026, imaging and observation of auroras have become increasingly popular during the current solar maximum, with social media flooded with spectacular images of these displays. These displays result from charged particles from solar storms interacting with Earth's upper atmosphere, exciting oxygen and nitrogen atoms to emit characteristic colors. The solar wind itself carries magnetic fields originating from the corona and extending throughout the solar system. Magnetic field lines of this interplanetary magnetic field connect planets, comets, and spacecraft in a vast electromagnetic influence network extending to the heliosphere, the boundary where solar wind pressure balances interstellar medium pressure. As we track solar storms propagating through the inner heliosphere, towards the end of September 2025, a special target attracted attention: an interstellar visitor passing through the system of space storms as it approached its first encounter with another world. Part 9. By Atlas was approaching in the early hours of 1st July 2025. The variable asteroid radar VAR early warning telescope system at the Ethel's asteroid station detected an unusual object moving contrary to background stars, but initial observations showed a faint comet-like object. However, orbital calculations quickly revealed its true nature. It was the 9th Atlas object confirmed as an interstellar traveler. In human history, the mysterious interstellar object Oumuamua in 2017 and the comet Borisov in 2019. Its name told the story of its discovery and prophetic significance, indicating it was the second interstellar object catalogued by the International Astronomical Union, while Atlas acknowledged the telescope system that discovered it. Unlike its predecessors, the 9th Atlas object appeared in a particularly favorable observation window, bright enough for detailed study, following an orbit keeping it near the ecliptic plane, and approaching under solar maximum conditions, offering an unprecedented opportunity to study how our star influences matter entering the solar system. The orbital characteristics of this visitor reveal its extraterrestrial origin. Its orbit is hyperbolic with an eccentricity greater than 1, indicating it has sufficient speed to escape the Sun's gravitational pull. An orbital inclination of about 175 degrees means it is flying. Alaska moves in the opposite direction to the planets, going against the usual traffic flow of the solar system. Current models show the object has a size somewhere from a few hundred meters, up to possibly 15 kilometers across. This estimate carries significant uncertainty, because direct imaging remains impossible. This visitor appears no more than a faint, bright spot surrounded by a cloud of gas and dust. Size estimates depend on assumptions about reflectivity, composition, and activity level of the object, all of which are unknowns for an object formed around another star. 3/10/2025 marks an important moment in science. Regarding interstellar visitors, Alaska will pass Mars at 0.19 astronomical units, about 28 to 30 million km. This close approach offers an unprecedented opportunity for detailed observation through Mars orbit missions including ESA's ExoMars Trace Gas Orbiter and NASA's Mars Reconnaissance Orbiter. Harvard astronomers have described this encounter as a secret rendezvous between an interstellar visitor and our neighboring planet. The high-resolution camera of the Mars Reconnaissance Orbiter can resolve objects as small as 30 centimeters on the surface. Mars will achieve a pixel scale of about 30 meters when pointing at Alaska during the closest approach, although this resolution will not reveal surface details of the nucleus. It can distinguish between a central condensed core and a more diffuse cometary tail structure. The scientific value of these observations goes far beyond simple imaging. Spectral measurements during the flyby can reveal the chemical composition of gases escaping from the nucleus as solar heating releases ancient volatile compounds such as cyanogen. Amateur astronomers worldwide have contributed important observations of Alaska throughout its approach. Initial reports indicate it is brighter than expected as it moves closer to the Sun. Although these preliminary light curves require careful calibration and confirmation, the visitor's position in the southern sky is favorable for observers in the southern hemisphere, although northern hemisphere observers can also track it in the early morning, Professional observatories continue to coordinate observation campaigns to describe changes in brightness, morphology of the tail, and spectral evolution. The visitor's orbit through the inner solar system offers many observation opportunities extending into early 2026. After passing Mars on 310, Alaska continues towards perihelion, the closest point to the Sun on 2910s, at approximately 1.36 to 1.4 astronomical units. This distance keeps it outside Earth's orbit, but still within the observing range of telescopes. 1910 marks the closest Earth approach of Alaska at about 1.8 astronomical units, roughly 270 million kilometers. By comparison, this distance is closer than Mars, at its farthest point from Earth, providing excellent observing conditions throughout late 2025 and early 2026. The visitor's activity near perihelion may reveal whether it follows typical cometary evolutionary patterns or exhibits features reflecting its interstellar origin. Tail morphology is one of the most fascinating aspects of Alaska's observations. Professional images show features of an ion tail pointing away from the Sun, consistent with typical cometary activity, while some amateur observers report dust structures pointing forward that seem to defy conventional physics. These seemingly paradoxical contradictions actually reflect different physical laws governing the formation of dust tails and ion tails. Dust tails form due to radiation pressure, the gentle but persistent force of sunlight acting on small particles, creating graceful curved tails. Ion tails form through completely different processes. When the solar wind strips electrons from gas molecules, creating charged particles that flow straight away from the Sun, along magnetic field lines. Uncertainties about size and composition around Alaska reflect fundamental challenges in the study of objects at interplanetary distances. Some media reports have speculated that the Atlas comet could be as large as 15 kilometers, but these estimates need to be considered cautiously until confirmed through thermophysical models. Combined with infrared observations of the object's activity level, the amount of gas and dust it produces also affects its apparent brightness, complicating size determination. The arrival of these visitors coincides with another spectacular astronomical event, promising to make October 2025 a memorable month for sky watchers. In early October, Comet Swan appears while Atlas Comet attracts media attention as an interstellar visitor. October 2025 also promises a second celestial show that could capture all the attention. Comet C 2025 A1. Swan was discovered in SOHO data by amateur astronomer Vladimir Bezukli on 11 and 12th of September, heading towards its closest approach to Earth on 20 and 21st October, likely to reach naked eye brightness during the same week, when Atlas Comet passes Mars. This discovery story has demonstrated the power of citizen science in modern astronomy. The Solar and Heliospheric Observatory, SOHO, continuously monitors the solar corona. Its instruments map the heliosphere, emissions throughout the heliosphere, and occasionally detect comets as they brighten when approaching the inner solar system. Vladimir Bezukli, scanning public SOHO data, noticed a brightening object not matching any known comet or asteroid. His careful analysis confirmed the cometary nature of the object and provided preliminary orbital calculations, indicating a long-period comet making its first recorded approach to the inner solar system in human history. Comet Swan reached perihelion, the closest point to the Sun, on 12th of September 2025, just days after discovery. This timing explains the initial rapid brightening that attracted Bezucli's attention. Comets usually brighten spectacularly when approaching perihelion, as solar heat releases volatile compounds from the nucleus, creating characteristic gas structures and tails. The orbital geometry of Comet Swan is favorable for observation in October from both hemispheres, although observers in the southern hemisphere initially will have better conditions. As October progresses, the comet's position becomes more favorable for northern hemisphere observers, offering excellent viewing opportunities for many astronomy enthusiasts. Current brightness predictions suggest a Comet Swan could reach magnitude 4 to 6 during its closest approach to Earth, bright enough to be seen with the naked eye under dark skies. Although binoculars or small telescopes will reveal more details of the coma and tail. However, these brightness estimates come with significant uncertainty, as comets are notoriously unpredictable, especially new comets making their first approach to the inner solar system. The timing coincidence creates a perfect convergence of astronomical phenomena. At the end of October 2025, the new moon phase, around 20 and 21 October, will eliminate moonlight interference that usually dims faint celestial objects. The annual Orionid meteor shower also peaks on those nights, caused by debris from Halley's Comet. Skywatchers may witness a bright comet, many meteors per hour, and the ongoing evolution of the zodiacal light, all in one ideal night of observation. Comet Swan is a long-period comet of the solar system, creating a stark contrast with the interstellar origin of Comet Atlas. Although both objects may contain similar volatile compounds, such as water, carbon monoxide, and carbon dioxide, they formed in completely different environments. Comet Swan condensed from material in the outer regions of our solar system about 4.6 billion years ago, and may have spent most of its existence in the Oort cloud, distant before being pushed towards the Sun by a gravitational disturbance. The scientific questions posed by each object are also different. The ALAS article provides insights into the chemical star system formation process between stars, and how cosmic radiation affects matter over journeys lasting millions of years. Meanwhile, the Swan comet provides information about the conditions in the early solar system and the composition of the WAP cloud. The opportunities for photography will be abundant for both professional astronomers and amateurs during the spectacular double comet event in October. Wide-angle cameras can capture both objects in the same frame, recording their relative positions, brightness, and tail structures for comparison. Time-lapse photography can reveal changes in the morphology of the comet head, tail direction, and overall brightness. The unpredictable nature of comet brightness variations adds to the fascination and uncertainty for observing prospects of some comets far exceeding brightness predictions, spectacularly developing magnificent tails, and becoming unmistakable objects even from light-polluted urban areas. Other comets disappoint by not being as bright as expected, or breaking apart under the influence of solar heat. The brief observational history of Comet Swan makes reliable prediction especially difficult. The potential for impressive tail development further increases the appeal of the opportunity to observe comets in October. Both dust and ion tails can become prominent features when solar wind activity remains high during the peak phase. Tail disconnection events, where Cassini severs the ion tail from the comet nucleus, can become visible in real time through telescope observations, providing rare insights into the physics of active space weather. Observers. Amateur comet watchers apply various techniques to monitor their changes, estimating visual brightness by comparing the comet's brightness with neighboring stars, providing data that professional observatories cannot collect. 10. Continuous photographic methods using digital cameras provide more accurate measurements while recording structural changes in the features of the head and tail. The question of whether Earth might encounter debris from the Swan comet further increases interest. If our planet's orbit intersects with the comet's dust trail, we might experience a minor meteor shower as particles enter the atmosphere. However, such events remain very uncertain for newly discovered comets. Spectral observations of both comets in October can reveal similarities and differences in chemistry, shedding light on their formation history. These chemical fingerprints provide evidence directly about their composition and formation conditions. Observing the two comets in October will be most favorable for those with dark skies and clear horizons. Pollution from urban lighting significantly reduces the visibility of faint objects, making rural locations more ideal. Binoculars usually allow better comet viewing than telescopes for casual observers. Wide-field binoculars show the entire comet in its context, rather than just magnifying small parts. 7x50 or 10x50 binoculars are optimal choices, providing enough light-gathering power to reveal faint details. The convergence of two bright comets in October 2025 offers an unprecedented comparative observation opportunity. Parallel observations can reveal differences in color, tail direction, and overall morphology, reflecting their different origins and evolutionary histories. Professional observatories worldwide have coordinated observation campaigns for both objects, ensuring comprehensive coverage across multiple wavelengths. The Hubble Space Telescope can obtain high-resolution images while radio telescopes can detect molecular emission lines. Safety considerations when observing comets are minimal. Comets do not pose any direct threat to observers and do not require any special protective equipment. Educational opportunities will multiply when two beautiful comets appear together in the sky under optimal viewing conditions. Schools, astronomy clubs, and public observatories often organize special observation events, promoting scientific knowledge while celebrating the wonder of cosmic phenomena as October 2025 approaches. The observatory has been prepared for an unprecedented month of astronomical activity. An interstellar visitor will pass Mars, a long-period comet reaching peak brightness, weather conditions, strong solar activity, and continuous aftershocks from earthquakes in Venezuela. The convergence of phenomena ranging from seismology to astronomy creates a timeline, challenging conventional assumptions about cosmic conjunctions. But before exploring deeper questions, we need to consider the laws that the human mind inevitably recognizes when dramatic phenomena converge. Part 11. Cosmic Coincidence or a Hidden Law. Let us review the timeline to see the remarkable convergence of events in late September and early October 2025. 23 September. Nova 6th, a 9th magnitude BA century explosion visible to the naked eye. 24th of September, a 6.2 magnitude earthquake occurred in Venezuela at 22:21 UTC. 25 September, Nova 6, 7994. Sagittarius exploded. A 6.3 magnitude earthquake continued to shake the same area in Venezuela just 5.5 hours after the first quake, followed by a 5.8 magnitude aftershock. Late September end models predict a coronal mass ejection will pass through the orbit of asteroid Atlas. 30 September. Interstellar visitor flies past Atlas. Passes Mars at a distance of 0.19 astronomical units on 22nd of October. Comet Soan approaches Earth closest, coinciding with the new moon and the peak of the Hen. Orionids meteor shower on 29th of October by Atlas. Perihelion at a distance of 1.36 astronomical units from the Sun. The temporal compression of dramatic events across multiple fields, comet explosions, earthquakes, solar weather, and the dynamics of objects approaching planets create a narrative structure that seems orchestrated. 2 stars explode within days. 2 major earthquakes occur within hours. Solar storms sweep through space within the same week. An interstellar object approaches Mars, while another comet reaches peak brightness. This concentration far exceeds mere coincidence, and almost reaches the threshold of cosmic synchronization. The human brain has evolved to detect meaningful patterns in complex environments, a cognitive ability that served our ancestors well. This pattern recognition structure operates automatically, scanning for connections that may indicate causation even when only correlation exists. The phenomenon of apophenia, a cognitive tendency to find meaningful patterns in random information, represents both a strength and a weakness of human cognition. Mainstream science offers clear explanations for the convergence of September and October. The U.S. Geological Survey confirms that no physical mechanism has been proven to link space weather with the occurrence of earthquakes. Professional seismologists emphasize that earthquake prediction remains impossible with current methods. Similarly, astronomers view novae as predictable outcomes of evolutionary processes, governed by physical laws of stars, not influenced by Earth or the solar system. Solar physicists study coronal mass ejections as natural consequences of magnetic field evolution under extreme solar conditions. The interaction between solar storms and cometary material represents a physical process of plasma that is well understood, not a strange phenomenon. However, accepting mainstream scientific views does not require us to deny the astonishing nature of this sequence of events. Sometimes the universe arranges itself in ways that make random coincidences become something almost poetic, even when the underlying mechanisms remain ordinary. The question posed is how we can reconcile strict scientific skepticism with wonder, inherently adopting a balanced approach that allows us to appreciate statistical convergence. While still respecting scientific limits, we can acknowledge that 2 novae, both reaching naked eye brightness within a few days, is a rare event without needing to invoke a causal link with earthquakes. We can observe that magnitude 6 earthquakes occurring within hours follow known laws of stress displacement that, without assuming solar weather effects, we can be amazed at the timing by Atlas. Approaching during solar maximum conditions. Understanding these are favorable observational conditions. Rather than a mystical coincidence, we can celebrate the convergence of two bright comets under optimal viewing conditions without concluding that cosmic forces have arranged this alignment for humanity's benefit. The power of media also amplifies the feeling that everything happens simultaneously through focused reporting and spreading on social networks. When many dramatic events occur within days, the news cycle and online discussions create echo chambers, reinforcing perceptions of their significance. Archaeological and historical evidence shows that humans have always sought cosmic meaning. In earthly events, ancient civilizations interpreted comets as omens, eclipses as divine displeasure, and coincidences between earthquakes and comets as supernatural messages. These cultural patterns persist in the modern context where scientific knowledge coexists with a deep psychological need to find meaning in clusters of random events. The challenge posed is to maintain scientific rigor while acknowledging the emotional and aesthetic impact of a remarkable convergence. We can admire the beauty of cosmic timing without abandoning critical thinking. Competing hypotheses deserve consideration simultaneously, provided we maintain a clear distinction between established science and speculative possibilities, interpretations of unrelated event clusters, but based on a solid physical foundation. Stellar physics explains nova explosions, plate tectonics explains earthquakes, solar physics explains CMEs, and celestial mechanics explains comet approaches. Each phenomenon follows well-understood natural laws and operates independently. Interpretations of a cosmic resonance enter a more speculative domain, suggesting subtle connections between phenomena not yet recognized by mainstream science. This view does not require abandoning physics, but proposes that our current understanding may be incomplete. Both perspectives can coexist intellectually, provided we maintain appropriate epistemological boundaries. Established science deserves priority, as it is supported by extensive observation and successful prediction. Speculative hypotheses deserve exploration, provided they are clearly distinguished from proven knowledge and generate testable predictions. Finally, the zodiac provides an additional context without demanding strange explanations. The Russell-Maffetone effect creates geometric conditions, amplifying the impact of space weather in September and October, making this period statistically more likely to produce significant geomagnetic activity. Seasonal patterns in earthquake occurrence have been reported in some regions, although mechanisms remain unclear and effects are often subtle. Cultural patterns provide narrative richness. Without requiring literal interpretation, comets have symbolized change, turbulence, and communication. The universe, throughout cultures over millennia, symbolizes the solidity of the Earth, while also revealing its dynamic nature. Stellar explosions illustrate the fierce beauty of cosmic evolution. These associations provide powerful narrative elements, resonating with profound psychological patterns while remaining independent of physical causes. This is an invitation to the audience to try to embrace different hypotheses openly, valuing both the rigor of science and the wonder of storytelling. We can enjoy a sense of synchrony as cosmic events converge without abandoning critical thinking. We can explore speculative connections while respecting established physical foundations. We can celebrate remarkable phenomena, while acknowledging the role of probability. Perhaps the most honest approach is to accept uncertainty while remaining open to future discoveries. Science advances through careful observation, hypothesis formulation, and rigorous testing, rather than hasty certainty about complex phenomena. The convergence of September and October provides a rich source for both scientific analysis and imaginative exploration, as long as we maintain clear distinctions between what we observe, what we hypothesize, and what we truly know. Delving deeper into these questions, there is a particularly speculative connection, worthy of careful consideration: the long-debated possibility that space weather can influence seismic activity on Earth through mechanisms still unclear. Part 12: Space Weather and Earthquakes. The idea that solar storms might affect earthquake occurrence is one of the most persistent and controversial hypotheses in space science for many decades. Researchers have reported statistical correlations between space weather phenomena and seismic activity. However, no widely accepted physical mechanism can explain how electromagnetic disturbances 150,000 cars away could trigger sudden faults in the Earth's crust. The most intriguing hypothesis recently comes from researcher Stefan Burns, who proposed that a decrease in solar wind density could create a type of electromagnetic vacuum capable of subtly altering the stress field of the Earth's crust. According to this model, when a dense, fast-moving solar wind stream suddenly gives way to a thinner, slower stream, the change in electromagnetic pressure on Earth's magnetosphere could theoretically propagate through complex mechanisms to affect stress accumulation on fault systems. This physical mechanism would involve multiple steps, each accompanied by uncertainty and diminishing effects. Initially, the change in solar wind density alters the shape and pressure of Earth's magnetosphere. Changes in magnetospheric configuration can modify electric currents flowing through the ionosphere. These current variations may then generate electromagnetic fields propagating into the Earth's crust, where they might influence piezoelectric effects in crystalline rock structures. Each step in this proposed causal chain involves extremely small effects, with magnetic field variations measured only in nanoteslas or stress changes thousands of times smaller than those required to trigger an earthquake, unless the fault system is already extremely close to failure. The theoretically linked mechanisms do exist, but their intensity appears insufficient to affect seismic activity under normal circumstances. What science has actually demonstrated is the existence of numerous claims of correlation, but a complete lack of evidence for causation. Studies over many decades have reported statistical links between solar flare activity and earthquake occurrence, between geomagnetic storm intensity and clustering of seismic events. These correlations often appear statistically significant when first reported, but often cannot be replicated when tested with other datasets. Publication bias further complicates the issue significantly. Studies finding positive correlations are more likely to be submitted, accepted, and cited than negative results, creating a false impression of scientific consensus. The official position of the U.S. Geological Survey (USGS), supported by international seismological organizations, asserts that there is no reliable evidence demonstrating a correlation between space weather and the occurrence of earthquakes, This conclusion is based on extensive statistical analysis comparing global earthquake data with space weather databases spanning multiple solar cycles. When appropriate statistical controls are applied, most reported correlations disappear or become insignificant. However, some researchers continue to explore more subtle potential connections, which may only operate under specific conditions. Electromagnetic induction represents another proposed mechanism, where strong geomagnetic storms can generate currents in conductive underground materials. But again, the intensity seems insufficient. Gravitational effects offer a more promising direction, although not through electronic mechanisms. Earth tides caused by the gravitational pull of the moon and sun have a clear influence on earthquake occurrence, with some studies showing seismic activity slightly increases during maximum tidal stress phases. These gravitational effects are well understood, measurable, and operate through established physical mechanisms. Conversely, planetary alignments, although popular in alternative theories, produce gravitational effects many orders of magnitude smaller than normal tides. The greatest challenge lies in separating physical relationships from truly random statistical phenomena. Earthquake occurrence follows complex statistical patterns, which can easily generate spurious correlations with any external phenomena. So, what would constitute convincing evidence for a link between space weather and earthquakes? Firstly, a proposed mechanism must be demonstrated to be physically plausible. Secondly, statistical relationships must demonstrate predictive skill far beyond random chance. Thirdly, any real connection is likely to be conditional, rather than universal, only operating in certain tectonic contexts. The earthquake swarm in Venezuela occurred during a period of increased space weather activity, providing an additional data point in the ongoing debate. However, isolated coincidences do not prove systematic relationships. If any real link exists, it is likely subtle and conditional, rather than dramatic and universal. Current seismological understanding shows earthquake timing depends primarily on local stress processes. External factors, whether from space weather or other sources, probably play only a very minor role compared to dominant tectonic forces. The most honest scientific view is to acknowledge both theoretical possibilities and experimental limitations. Subtle connections between space weather and seismic activity cannot be completely ruled out, but there is no convincing evidence that such connections are strong enough to significantly influence earthquake occurrence. Future research should focus on identifying plausible mechanisms before seeking statistical correlations for earthquake forecasting, and realistically assessing risk. Monitoring space weather does not provide useful information. Building codes, emergency planning, and public safety measures should continue to be based on established seismological knowledge. When exploring these terrestrial links, an even more speculative question arises: can energy from distant explosions affect Earth's climate over longer periods? 013 Stars and Climate. The idea that explosions, stars can affect Earth's climate operating on energy scales, distances and times vastly different from the space weather earthquake hypothesis. While nearby supernovae in theory could affect our planet, ordinary nova like V19 BA year century, and V 79994 Sagittarius, much weaker and much farther away, cause no short-term impact on Earth. It is almost impossible to establish the pattern of related events with uncompromising accuracy. A typical nova explosion releases energy equivalent to the total output of the Sun over about 10,000 years, approximately 10 to the power of 43 ergs. This number sounds enormous, but this energy source spreads out spherically, thinning according to the inverse square law, as it travels through space, V19, BA year century, perhaps several thousand light-years from Earth, meaning its explosion occurred millennia ago. By the time the energy flow from the explosion of this ancient star reached the solar system, it had diminished to a level equivalent to the light of a bright star, beautiful to observe, but completely insignificant in terms of impact on climate or atmospheric chemistry. The final energy reaching Earth from both September novae combined is less than the radiation you receive from a torch held at arm's length. To put this in a climate context, the total energy Earth receives from both novae would not be enough to warm a cup of coffee. Compare this with nearby supernova explosions, which are real candidates for climate impact. On geological timescales, a supernova occurring within about 55 light-years can carry enough high-energy radiation to significantly alter atmospheric chemistry. Gamma rays and X-rays from such an explosion can destroy significant parts of the ozone layer, allowing increased ultraviolet radiation and potentially causing mass extinction events. Some researchers have proposed a link between nearby supernovae and extinction events in history, such as the late Ordovician extinction event, about 450 million years ago. Although the evidence remains controversial, the proposed mechanisms involve complex atmospheric chemistry, rather than simple thermal warming. Cosmic rays, that is, high-energy particles accelerated by supernova shock waves, also provide another potential channel for stars' influence on Earth's climate, although again on very different timescales. Media stories often lump together types of nearby star explosions, or confuse actual threats with imagined ones. The timing correlation between star explosions in September and earthquakes on Earth is fertile ground for building causal stories, but the energy scales involved make any direct connection physically absurd. However, scientific research on star explosions and climate remains a fascinating field as long as it focuses on feasible mechanisms operating on appropriate timescales. Isotope evidence in geological formations sometimes preserves traces of cosmic ray bombardment, such as iron-61. Radioactive isotopes mainly produced in supernova have been found in deep-sea sediments and ice cores. The detection of iron-60 shows Earth experienced increased cosmic ray exposure about 2 to 3 million years ago. But the question, whether this increase actually affected climate, remains open. For the September 2025 novae events, any climate impact remains purely academic and almost zero. These distant star explosions contribute no significant energy to Earth's radiation budget, do not alter atmospheric chemistry, and do not affect detectable climate variables. The broader lesson is to maintain an astronomical perspective and the distinction between dramatic cosmic events and measurable impacts on Earth. Our planet's climate is controlled by changes in solar radiation, atmospheric composition, ocean current patterns, and volcanic activity. Processes on Earth and within the solar system operate over time spans, from a few years to millennia. Although astronomical factors cannot be completely ruled out on a geological timescale, they remain insignificant compared to the dominant forces shaping the evolution of Earth's climate. The psychological appeal of linking distant stellar explosions with phenomena on Earth reflects a deep human need to seek meaning and patterns in seemingly random events. These cognitive tendencies have served our ancestors well in detecting real correlations in their environment, but they can also cause us to see meaning in the random convergence of unrelated phenomena as we explore connections on Earth with cosmic events. Our attention now returns to the interstellar visitor, which may offer the most direct and immediate opportunity to study how the solar system interacts with matter from other stellar regions. Part 14. Interstellar Visitors. As cosmic probes, alas, not merely curious objects, from interstellar space, it may be the most sensitive natural probe we have ever had to study how the Sun interacts with matter formed around other stars, while Oumuamua left too quickly for detailed study and Borisov remained relatively distant. This third interstellar visitor brings unprecedented opportunities to observe the effects of solar weather on matter that has wandered for millions of years between star systems. The orbital geometry alone makes Borisov extraordinary for heliospheric science. Unlike previous interstellar objects, this visitor passes through the ecliptic plane, the plane where solar wind density, magnetic fields, and space weather activity reach their highest intensity. It is approaching during the peak phase of the 25th solar cycle, when the frequency of coronal mass ejections peaks and the complexity of the solar magnetic field reaches maximum chaos. Imagine comets as natural magnetometers and floating plasma diagnostic tools in space. Their ion tails provide tangible evidence of invisible magnetic field lines within the solar wind, changes in direction, brightness, and morphology of the tail reveal information about space conditions. Researchers have used comets in the solar system as sensor tools for many decades. Borisov has the potential to extend this capability to matter with a completely different formation history and chemical composition. If coronal mass ejections alter its behavior, we are witnessing for the first time the recorded interaction between the Sun's magnetic field and matter from another star system. The flyby of Mars on 310 offers a unique observational perspective that ground-based telescopes cannot achieve. Into the orbits of ESA's ExoMars Trace Gas Orbiter and NASA's Mars Reconnaissance Orbiter. Icarus will be observed from a distance of only 0.19 astronomical units, approximately 28,000 kilometers. The high-resolution camera of the Mars Reconnaissance Orbiter will achieve a pixel resolution of about 30 kilometers when pointed at the interstellar visitor. Although it cannot reveal surface details, it can distinguish between a compact solid nucleus and a more diffuse gaseous envelope. Simultaneous observations from Mars orbiters and Earth-based telescopes will provide parallax measurements to determine scale and the activity level of this visitor more precisely. Spectroscopic capabilities from Mars orbiters further enhance the scientific value of detecting gases such as CN, CO or CO2, which will provide evidence directly about the chemical composition of the object and how solar heating releases volatiles from interstellar ice. Observatories worldwide on Earth continue coordinating observation campaigns to monitor brightness changes, spectral evolution, and morphological variations as Atlas comet flies responding to solar wind conditions. Amateur astronomers contribute important observations, providing the temporal resolution needed to detect short-term variations that can be correlated with specific space weather events. Precedents with dramatic interactions between the CME and cometary coma from observations. Comet Encke's tail broke off in 2007. That event demonstrated the violent reality of reconnection of magnetic fields between solar plasma and cometary material. If similar disconnection events occur with Atlas comet, they could provide profound insights never before seen into how the solar magnetic field interacts with matter. Between comets, scientific questions go beyond simple space weather interactions. Atlas comet carries isotopic signatures from the comet system of its birth that may reveal information about synthesis processes of comet nuclei and chemical evolution in other parts of the galaxy. Solar heating releases these ancient volatiles, offering the first opportunity for us to analyze cometary material spectroscopically at close range. Observations may reveal whether millions of years of exposure to cosmic rays have altered the chemical composition or physical structure of this object. Compared to comets in the solar system or not, the timing of Atlas observations coincides with breakthroughs in monitoring and modeling space weather. Atlas comet may also serve as a test case for our planetary defense capabilities. Although it poses no impact threat, the orbit and response of this object provide an opportunity to validate detection and characterization methods that will be essential if a hazardous interstellar object ever approaches Earth. The broader significance of science on interstellar visitors also extends to astrobiology and the search for extraterrestrial life. If Atlas comet carries organic compounds or prebiotic materials, spectral analysis could reveal whether the chemical building blocks of life are widespread throughout the galaxy. Observation capability, extending to early 2024, ensures that scientific investigations can continue long after the initial excitement. As we prepare for October, the convergence of events, a visitor to the comet, solar maximum conditions, and international observation campaigns create potential for discoveries that could reshape our understanding of our place in the universe. Part 15. Heading towards October and beyond. Mark important dates on your calendar. 2021 and 29th of October. Highlight 1910. 2. These days represent milestones, potential breakthroughs in our understanding of interstellar visitors, space weather interactions, and the broader cosmos. The new month marks the closest approach of comet Atlas to Mars at a distance of 28,000 kilometers. This is the first time in history an interstellar visitor has been observed by spacecraft orbiting another planet. 20 and 21 October promise another celestial spectacle, when comet 2I Borisov reaches its closest approach to Earth. This timing perfectly coincides with the new moon and the peak of the Yang Orionid meteor shower, creating optimal dark sky conditions. 2910 is the hottest time for Atlas comet as it reaches perihelion, the closest point to the Sun. This approach will expose it to conditions, with temperatures capable of releasing volatiles locked away for millions of years. 1910. 2 marks the closest distance of Atlas comet to Earth, at about 270,000 km. This distance is closer than Mars at its farthest point, providing excellent observation conditions. This distance is closer than Mars at its farthest point, providing excellent observation conditions throughout the winter months. Distinguishing between what can be expected and what is merely hype requires careful adjustment of public expectations. Comets and interplanetary objects are often very unpredictable, with the most likely scenarios occurring, including gradual brightness changes and morphological variations, detectable through telescopes rather than spectacular phenomena visible to the naked eye. The most important results may come from spectral analysis, revealing chemical composition rather than dramatic visual changes, attracting media attention. Space weather monitoring continues at high intensity, as Solar Cycle 25 maintains peak activity levels until the end of 2025. The Russell-McLaren effect in autumn increases the likelihood of significant geomagnetic activity, potentially creating spectacular auroral displays. Earthquake monitoring in Venezuela continues as aftershock sequences progress following major earthquakes in late September. Nova monitoring also continues for both V19b Century and V7.994 Sagittarius as they fade over the next few months to years. The story we will tell about October and beyond depends greatly on separating observational results from speculative interpretations of each phenomenon, from planetary or interstellar objects, space weather activity, seismic monitoring, to nova evolution. All follow established physical laws, operating independently. However, this convergence deserves to be recorded and analyzed as a remarkable example of how the universe sometimes arranges dramatic events in brief periods. Whether this focus is a coincidence or subtle physical connections we do not yet understand remains an open question, which future observations may help resolve. A call to action for the audience is to enjoy these celestial events safely while maintaining realistic expectations and consulting authoritative data sources such as NASA, ESA, OSGS, and NOAA. Amateur participation in these observations provides meaningful opportunities to contribute to scientific understanding, while experiencing the wonder of cosmic phenomena directly. The overarching question of all these observations is whether the temporal concentration represents something more than statistical coincidence. If this convergence seems strange, perhaps it is because the usually separate timescales of stellar evolution, geological processes, solar activity, and encounters with interstellar objects have overlapped rarely within a human lifetime. The scientific promise is not limited to immediate observations in October, but extends to deeper analyses later, when data from Mars orbiters and extended monitoring results become available. What is certain is we are witnessing a convergence of events, spanning cosmic explosions to earthquakes to encounters with interstellar visitors. It is a reminder that we live in a dynamic and more connected universe than our daily experience often reveals. These achievements must also be accompanied by acknowledgement of the inherent uncertainty in all phenomena while celebrating the ability to observe, measure, and seek understanding of our place in the universe. which occasionally shows the ability to surprise, inspire, and humble us. Ultimately, perhaps the real story is not whether these events have a hidden cosmic connection, but that we live in the first generation in human history, capable of detecting, monitoring, and studying such an astonishing convergence across all domains of space and time. It is a perspective, a privilege, that no previous civilization on Earth has ever had.